Hello, I'm Javier Serrano. I'm PhD in computer science and automation. I am a full-time researcher at Attostructura. I'm going to start talking about the theoretical discussion of high harmonic generation that we use for our simulation. Then I will comment the platform that we have used for simulation, the computing cluster that we use to run the simulation, then the performance optimization that we have had to implement to be able to run complex simulations. And finally, I will show our progress applying artificial intelligence techniques to high harmonic generation. Here we have the process of high harmonic generation that Carlos has already commented. We have an infrared laser pulse with a short duration of few femtoseconds that is targeted towards a gas jet or sometimes a solid like a pin, and that generates an ultraviolet or ultraviolet pulse. But the emission is produced in individual atoms or molecules inside this following this microscopic process. Initially, there is ionization, then an acceleration of the electronic wave packet, and finally a recombination that generates this harmonic. And to match experimental results, we have to calculate the emission in thousands, sometimes in millions for different atoms, to finally, and then the propagation of these individual emissions to finally calculate the total field that we'll see in a detector. And we have different methods to calculate this microscopic emission in different scenarios. For example, we use the time-dependent equation in gases. We can do it with a single active electron in 2 and 3 dimensions, or with 2 active electrons. We can also calculate high harmonic generation in graphene using the TDSC coupled with tight-binding band structure. When this method is quite time-consuming, so in many of our simulations, we have to rely on the strong field approximation that is faster and still provide the results. And we can use it in different atoms with different atoms and molecules. Finally, we can calculate high harmonic generation in multi-layer 2D materials thanks to a code developed by Antonio Picón at the Universidad Autónoma de Madrid that collaborates with us. And on the other hand, we have the macroscopic description. We have to calculate the propagation of the driving field, and we have two different implementations. One of them only takes into account linear effects, Carlos has commented, and we have code developed in the group. And we have a more recent implementation that takes also into account nonlinear effects based on a propagation code based on the slowly evolved wave approximation developed by Julio San Romani and Peter Costa. Sometimes we use one implementation, sometimes we use the other one, because in some simulations, nonlinear effects are more relevant than in others. And finally, to calculate the propagation of harmonics, we use the electromagnetic field propagator that is described in this paper from Carlos Garcia and Bull. And with this theoretical background, we have implemented a software framework for high harmonic generation that is a multi-platform. We can use it in Linux, MacOS, and Windows. And it has a modular design that supports C, C++, and Fortran modules. That means that we can have different implementation for all steps of whole simulation. So we can have different implementation for propagation of the laser field. We have the different implementation for the microscopic high harmonic generation, and different implementation also for the propagation of harmonics. The framework is highly configurable at runtime. That means that we don't have to rebuild the software to run very different simulations. So we can, with a single program, simulate the high harmonic generation in the screen and also in gases and many circumstances. And the main features of our framework that we can highlight is that it allows to use experimental and simulated driving beams, different target configuration, different detector configuration, and it also has some features that allow to analyze the result. Well, since this is a very modular software, we have put the independent modules to do this task. We have a module to calculate the linear propagation of the time field and nonlinear propagation, and all high harmonic generation methods that I have commented before. And additionally, we have some tools that allow to optimize our simulation. For example, we have the brute force tool that allows to run a batch of simulation with different combination of values for different parameters of the simulation to find the best combination for a specific purpose. When the number of combination is too high to run all of them, we have a genetic algorithm that does the same job, but without having to run every simulation, only some of them, more or less intelligent, looking for the best case. And we have also a graphical application, as you can see here, in which we can change every parameter of the simulation. We can see some basic graphs with the driving field, the harmonics generated in a specific point, textual information. And despite this tool is already quite useful, it requires a deep knowledge of our framework. So we are working on a new tool, graphical, that we have called to Pack 2D. In this new tool, we expect to implement an assistant that will give the user in the configuration of the different steps of the simulation, the driving field, the target, the harmonic generation, the detector, and in each step, it will show textual information. It will show detailed graphs about what happens in that step. It will show the parameters, but not with external names, but more understandable for an external developer. And we expect to also include some tools to post-process results, analyze results. Do not have to rely on MATLAB scripts like we are doing it. Well, here you can see the computing cluster that we use to run most of our simulations. It has at the moment 12 computing nodes. 8 of them have been funded by Attostructura project. Each node has 2 insertion processors. They have between 18 and 24 physical cores per processor and 192 gigabytes of RAM. We also have 3 GPU boards compatible with technology NVIDIA CUDA that we use to accelerate some calculations. In total, we have 3 GPU boards. 2 of them are NVIDIA A30 that we use to calculations with global precision, and one NVIDIA RTX 3080 that is more suitable for single precision calculation. All nodes are high-speed connectivity thanks to InfiniBand and 10 gigabit Ethernet interface, which is quite useful to run MPI simulation, MPI job for our students. And also we share the available computing time among all developers in the project using the Slack workload map. But even in these powerful computers, or even in supercomputers like the one in the Supercomputing Center of Barcelona that we have already used for this project, there are simulations that we are still unable to run in a reasonable time. So we are continuously working in performance improvements, so to be able to run more and more complex simulations. For now, we have added support for OpenMP and MPI in all frameworks, so all microscopic simulation can run in parallel. And we have focused our efforts in the TDSE implementation. We started with an implementation that worked with a single thread that required more than 1 hour to calculate the emission in just one atom. Then we parallelized it with OpenMP, and we reduced that time to 30 minutes. And then we started a new implementation from scratch using NVIDIA CUDA that now allows us to compute one atom in about 2 minutes. And taking advantage of this new implementation, we were able to generate a training set for a neural network that now allow us to calculate each atom in 0.1 seconds. 0.1 seconds per thread. And still we can parallelize this implementation in our framework. So in a supercomputer, we can calculate at the moment with the TDSC thousands of atoms per second. The only disadvantage that the neural network is that it's only valid for cases related to the training data that we have used. Some parameters have to be fixed. And this is how we have built this neural network. We have generated a training data with our framework, exactly 80,000 different calculations. And then we have built a neural network using Python, the development environment in Jupyter Lab, and the libraries Keras and Attostructura. When we have trained the neural network and we have with the neural network working, we have built a new model for our framework that allows us to use the training neural network inside our framework like any other high harmonic generation model. Here you have a picture that shows the progress of the training of one of these neural networks that shows that we reach a mean square error of 10 to minus 6. That is quite good for our simulation. And the result is that we have achieved highly accelerated SFA and TDSC pulses for pulses with different amplitudes. So other parameters like the pulse duration and so have to be fixed, but we can change the amplitude and phase. And that allow us to calculate to get macroscopic results in minutes with millions of pulses. Here we have an example of high harmonic generation in one atom in the time domain and the frequency domain. There are two lines here. One is the result of the TDSC, and the other one the result of the neural network. And they almost overlap. And here in the frequency domain, we can see that they start diverging and at the level of 10 to minus 4, 10 to minus 5. And we have used this neural network to calculate a macroscopic high harmonic generation in a vortex beam. We have selected this case because in a vortex beam we have all different possibilities for the phase of the pulse, and we have also all the different intensities that allows our neural network. So using this pulse, we can take advantage of all the input space of our neural network. And here we have the result of the 17th harmonic with 250,000 atoms calculated with the Stockholm approximation and with a neural network trained with the same algorithm. As you can see, both results are almost identical. And here is the most important, that is the result of the same simulation, but using a neural network trained with the TDSC algorithm. So for the first time, we have been able to simulate macroscopic high harmonic generation with time-dependent historic equation. And we hope to continue using these techniques to accelerate the calculation and also for other goals in the project. And that's all. You have any questions?